Hi, my name is Julie, and today I'm going to give you a presentation on spin orbit qubits. So today we are going to delve into the spin qubit orbit qubits, the cutting edge in quantum computing technology. Today we embark on a journey through the quantum realm where computing transcends traditional boundaries, leveraging the enigmatic principles of quantum mechanics. At the heart of this revolution are spin-orbit qubits, a promising new class of quantum bits. These qubits are not just mere particles, they are the harbingers of a new era where computing power is exponentially enhanced. Cryptography becomes unassailable, and complex systems are simulated through the unparalleled accuracy. The potential implications of harnessing this technology are vast and transformative. Let's dive into this fascinating world and explore how spin orbit qubits are poised to redefine what's possible in quantum computing. In these slides, we delve into the why behind spin orbit qubits and the profound impacts they promise. Firstly, let's talk about computational power. Quantum computing, particularly through spin orbit qubits, breaks free from the classical computing constraints, enabling us to process information at an unprecedented scale. Next, we look at cryptography. In an era where data security is paramount, quantum computing offers a form encryption that is theoretically unbreakable, setting new standards in digital security. Moreover, the realm of complex simulations stands to be transformed. Imagine the ability to simulate molecular structure and or drug interaction accurately and efficiently. Spin orbit qubits could make this a reality, opening new frontiers in material science and medicine. The implications of these advancements are vast and varied, extending across different sectors. In industry, they promise to revolutionize fields such as computing, finance, and logistics. In the realm of science, they accelerate research, offering new insights in the disciplines like physics, chemistry, and biology. And on a broader scale, they hold the potential to just drastically improve our social technological infrastructure, leading to breakthroughs that could significantly enhance our quality of life. In this slide, we delve into the quantum landscape by comparing spin orbit qubits with other leading technologies in quantum computing, traditional quantum dots, superconducting qubits, and trapped ions. Starting with the traditional quantum dots, they offer precise control and well understood framework. Yet they struggle with decoherence and scalability, limiting their practical utility in larger quantum systems. Moving on to the superconducting qubits, the workhorses of many existing quantum computers. They allow for rapid operations and are already being used in constructing quantum circuits. However, their need for near absolute zero temperatures and vulnerability to environmental noise are significant drawbacks. Then we have trapped ions, renowned for their long coherence times and high operational fidelity, making them excellent for precision tasks. However, the complexity of the required apparatus and the scalability remain as hurdles. Lastly, we introduce our protagonists, the spin orbit qubits. They stand out by potentially offering longer coherence times and the ability to operate at higher temperatures than many competitors. Though still an emerging technology, they face their own set of challenges, particularly in fabrication techniques. Each of these technologies has its strengths and weaknesses. Our aim is to understand where spin orbit qubits fits within the landscape and how they might address the limitation of existing technologies. And let's take a moment step back and explore the historical landscape that has shaped the development of spin orbit qubits, a journey that spans over decades. In the 1990s, foundational concepts of quantum computing began to take shape, setting the stage for a new era in computation. Fast forward to the 2000s, scientists discovered spin orbit interaction in semiconductors, paving the way for the first experimental realization of spin orbit qubits in the early 2010s. As we progress through 2015 and to 2018, there was significant enhancements in controlling these qubits, along with improvements in their coherence times, marking a period of rapid development and understanding. As you can see, these are some spin-orbit qubits historical overview. Here you can see some recent advancements and current frontiers. Here you can see some fundamentals of quantum mechanics and spin orbits. First, we have quantum superposition represented mathematically as psi equation, where alpha and beta are probability amplitudes for the qubit states. This principle allows us our qubits to exist in states that's both 0 and 1 simultaneously, an aspect that's at the core of quantum computing's power. Next is quantum entanglement, a phenomenon where pairs or groups of qubits become interconnected such that the states of one directly influence the states of another, no matter the distance separating them. An example is this equation, phi entanglement. Let's talk about the spin-orbit interaction, which is central to the operation of spin-orbit qubits. It's described by the Hamiltonian equation as we see in this slide, HSO. This equation encapsulates the interaction between an electron spins and its orbits, facilitated by electric fields. This interaction is what allows us to manipulate qubit states efficiently, offering a faster and a more scalable approach to quantum computing compared to magnetic field control. To the intricate world of spin-orbit qubits, where the confluence of quantum mechanics and material science opens up new frontiers. In this slide, we're breaking down the architecture that underpins these qubits. At the core of spin orbits is a quantum dot, essentially a nanoscale prism for electrons, created using precise electric fields. The potential where confining this electron can be described by this equation, V equation, dictating how electrons are spatially confined within the quantum dot. The uniqueness of spin-orbit qubits largely stems from the Rashba and Dresselhaus interaction, captured by the Hamiltonian's HR equation and HD equation, as we see in these slides. This formula illustrates how the spin of an electron interacts with its orbital movements, pivotal to manipulating qubit states. Control in this nanorealm is achieved through the application of gate voltages, modifying both the spatial confinement and strength of spin-orbit coupling. This magic of electric dipole spin resonance comes to life with F equation, F-Rabi, showcasing how we can achieve precise control of the qubit's spin states using electric fields instead of magnetic ones. Let's delve into the heart of spin-orbit qubits, their operating principle, a synthesis of quantum mechanics and technology that powers quantum computation. Firstly, the quantum dots at the core of our qubits have energy levels, which we manipulate using external voltage. The energy of these levels can be expressed as E equation, illustrating how these levels shift in response to change in environmental and control inputs. But how do we control the spin, the quantum bit itself? This is where the magic of spin-orbit interaction comes in, crafting an effective magnetic field, denoted as B equation, as we see in this slide. This internal mechanism allows us to alter the spin directions by purely electrical means, a feat not possible in traditional systems. Central to operating these qubits are Rabi oscillations triggered by alternating electric fields, swinging the qubits between their quantum states. The oscillation rates, or Rabi frequencies, given by F equation as we see in this slide, dictating how quickly spins can be flipped, a crucial factor in quantum computation speed. Finally, how do we read our quantum information? Through spin state detection techniques that leverage the Pauli exclusion principle. By observing changes in electrical conductivity, we can deduce the spin states, completing the cycle of quantum information processing. Each step in this process reflects a dance of physics and engineering, bringing to life the subtle art of quantum computation through spin-orbit qubits. Let's talk about the state of the art in spin-orbit qubits. Firstly, a significant leap has been made in terms of coherence times. The duration a qubit maintains its quantum states. Thanks to the advancements in material science and qubit design, we have seen coherence times increase to T2 conjugate equals 100 μs, enhancing the stability and reliability of quantum information processing. When it comes to scalability, an area crucial for the future of quantum quantum computing, strides have been made in interconnecting multiple spin-orbit qubits, forming the building blocks of larger quantum systems. This is coupled with significant progress in integrating these qubits with classical electronics, bridging the gap between quantum and conventional computing. So how about the control and the manipulation precision? High fidelity operation with error rates below 1% have been achieved thanks to the enhancements in electric dipole spin resonance method, allowing for rapid and accurate qubit rotations. Moreover, the practical application of these qubits have been realized, with complex quantum algorithm being successfully implemented. This algorithm, along with sophisticated quantum simulations, showcase the potential of spin-orbit qubits to solve problems far beyond the capability of traditional computers. This slide paints a picture of a rapidly evolving technology poised to redefine what's possible in quantum computing. Now let's talk about the challenges for further development. First and foremost are the hurdles in the material science and fabrication. The quest for uniform high-quality materials is crucial as we aim for qubits that perform consistently and reliably. Furthermore, the push towards nanometer precision in qubit fabrication presents its own set of technology trials. Then there's the ever-present specter of decoherence, the loss of quantum information. Environmental factors such as thermal noise and electromagnetic disturbance pose significant threats to qubit stability. Coupled with this is the need for sophisticated quantum error correction techniques, essential for maintaining qubit coherence over practical operation times. Scalability and integration pose additional challenges. As we envision quantum systems with increasing numbers of interconnected qubits, ensuring consistent and reliable interactions become more complex. Moreover, integrating this advanced quantum system with classical electronics for control and readout necessitates breakthroughs in hybrid system design. Lastly, control and readout efficiency remain pivotal. Enhancing the precision and speed of gate operation is crucial for accurate qubit manipulation. Similarly, advancing the speed and reliability of readout techniques is paramount for the practical utility of quantum computing. Let's talk about future prospects and applications. In the realm of quantum computing, we are not just iterating on existing technology, we are working toward universal quantum computers. They aren't just faster computers, they are machines that can solve problems currently deemed unsolvable, unlocking mysteries in physics, chemistry, and mathematics. Beyond computing, envision quantum networks, a new frontier of communication, enabling not just faster, but also fundamentally secure connections across the globe, leveraging quantum entanglements. In healthcare, the implications are profound. Imagine the speed of drug discovery with quantum simulations, allowing us to understand complex molecules and reactions in fractions of the current time. Similarly, in material science, we're looking at the ability to design new materials from the atom up, tailored for specific applications, from energy storage to medical devices. For a future application can be also shown on cryptography and security. Uh, for quantum cryptography, developing unbreakable encryption methods using quantum principles and security data transmission by implementing quantum key distribution for impenetrable communication channels. And let's not overlook the impact on artificial intelligence and machine learning. Quantum-enhanced algorithms hold the promise of handling vast data sets with unprecedented speed and precision, opening new avenues in everything from climate modeling and financial analysis. As we venture forward, the journey with spin-orbit qubits is just beginning. It's a path that leads to new discoveries, new technologies, and potentially a new understanding of the universe itself. As we conclude our journey into the realm of spin-orbit qubits, let's reflect on the significant strides we have observed in this field. Spin-orbit qubits represent a pivotal innovation in the quantum computing landscape, offering unique advantages such as enhanced coherence times and the groundbreaking ability to control quantum states electrically. However, our exploration also highlights the various challenges that lie ahead. The implication of mastering spin-orbit qubits extend far beyond the realms of computing, from revolutionizing cryptography to pioneering new avenues in medical research. The potential applications are as vast as they are profound. And that's all for my presentation. Thank you.